All right, so here we'll be talking about chapter 13, um, temperature, kinetic theory, and gas laws. As you can see for the outline, we'll go over temperature, defining it, converting it between Celsius, Fahrenheit, Kelvin, defining thermal equilibrium, stating Zero's law of thermodynamics. We'll go into some thermal expansion of solids and liquids, the ideal gas law with kinetic theory as well. So a lot of these, a lot of chemistry related subjects as well, just like it was for chapter 11 and 12. So we'll go ahead and get started. So first, temperature. The concept of temperature has evolved from the common concepts of hot and cold. Human perception of what feels hot or cold is a relative one. For example, if you place one hand in hot water and then another in cold water, then place both hands in tepid water, the tepid water will feel cool to the hand that was in the hot water and warm to the one that was in cold water. The scientific definition of temperature is less ambiguous than your senses of hot and cold. Temperature is operationally defined to be what we measure with a thermometer. Many physical quantities are defined solely in terms of how they are measured. We shall see later how temperature is related to the kinetic energies of atoms, molecules, and more physical explanation. So two accurate thermometers, one placed in hot water and the other in cold water, will show the hot water to have a higher temperature. If they are then placed in tepid water, both will have identical readings within measurement uncertainties. And that just means within that thermometer's, specifications. So for figure one, we have a thermometer here. In a typical thermometer like this one, the alcohol with the red dye expands more rapidly than the glass containing it. When the thermometer's temperature increases, the liquid from the bulb is forced into the narrow tube, producing a large change in the length of the column for a small change in temperature. So here you'll see this little red line, which is the liquid, go up and down. If you're in a hotter temperature, in a higher temperature, it'll be hotter. It'll be on the higher end of the thermometer, and vice versa for the lower temperatures. For here, we have each of these 6 squares on the plastic liquid crystal thermometer contains a film of different heat-sensitive liquid crystal material. Below 95 degrees Fahrenheit, all 6 squares are black. When the plastic thermometer is exposed to temperature that increases to 95 degrees Fahrenheit, the first liquid crystal square changes color. When the temperature increases to above 96.8 degrees Fahrenheit, the second liquid crystal square also changes color, and so forth. So each one of these, can't really tell here, but they'll change colors as you progress. Here we have another figure with relationships between Fahrenheit, Celsius, and Kelvin temperature scales right into the nearest degree. The relative sizes of scales are also shown. So here we have Fahrenheit. We know that for freezing water, we have 32 degrees Fahrenheit, but it's the same as 0 degrees Celsius, and that's also the same as 273.15 Kelvin. So each one of these has a relationship between them. For boiling water, 212 for Fahrenheit, 100 for Celsius, and 373.14 for Kelvin. And we'll go into the interpretation of each one of them and the equations to go from one to the other here shortly. So here are the conversions. For Celsius to Fahrenheit, we have this equation here. We have 9 over 5 T of the temperature in Celsius plus 32 degrees. Remember, we want the temperature in Celsius here to go into Fahrenheit. So we'll add 32 degrees, which you can see from here is the case. If we're starting at 0 degrees Fahrenheit, or 0 degrees Celsius, and we add 32, that'll get to the freezing water for Fahrenheit. For Fahrenheit to Celsius, we do the inverse, 5 over 9, temperature in Fahrenheit minus 32 degrees. So if we go back here, if we're trying to go to Celsius, we'll do the 32 times the 5 over 9 minus the 32. For Celsius to Kelvin, we should do the temperature in Celsius plus 273.15. So right here, if we have 0 degrees Celsius and we're trying to convert to Fahrenheit or to Kelvin, all we have to do is add that 273.15. And you see that in the boiling water as well. We have 100 plus 273.15 will give us the boiling point for water in Kelvin. For Fahrenheit to Kelvin, we have 5 over 9, temperature in Fahrenheit minus 32. So you see that here, this part of the equation is exactly the Fahrenheit to Celsius conversion. And then we add the plus 273.15. And from Kelvin to Fahrenheit, it's inverse of that. You do the 9 over 5 here, temperature in Kelvin. You have to subtract the 273 here first, and then add the 32. So essentially, these two are combinations of the ones up here. And if you want to simplify it just a little bit more, so you can have all those notations for them, you can write them like this. So temperature in Kelvin, temperature in Fahrenheit, temperature in Celsius. Either way works. So for here, room temperature is generally defined as 25 degrees C, so 25 degrees Celsius. What is the room temperature in Fahrenheit? So for this one, we go from Celsius to Fahrenheit. So we use this equation. You would plug in 9 over 5 times the 25 degrees here plus 32. And then going from Celsius to Kelvin, you would just plug in to this equation. So 25 plus 273.15. And that's it. Those are the direct conversions for those. So in this figure, this image of radiation from a person's body, an infrared thermograph, shows the location of temperature abnormalities in the upper body. Dark blue corresponds to cold areas, and red to white corresponds to hot areas. Humans beings have been known to survive with body temperatures within a small range, from 24 degrees C to 44 degrees C, 75 degrees Fahrenheit to 111 degrees Fahrenheit. The average normal body temperature is usually around 37 degrees Celsius, so around 98.6 Fahrenheit. And the variations in this temperature can indicate a medical condition, a fever, an infection, a tumor, or circulatory problems. So pretty standard image here. For this image, we have a graph of pressure versus temperature for various gases kept at a constant volume. And we'll get into how to figure those out here in a minute. Note that all of these graphs extrapolate to 0 pressure at the same temperature. So here we have 0 pressure at this temperature, negative 273.15 Kelvin, right? But as we go out, they don't identify which gas this is, but the higher the pressure, the higher the temperature. Okay, each gas has its own variation between pressure and temperature. So if we were to name this, helium or whatever gas you would want, this would be the correlation between them. So the zeroth law. Thermometers actually take their own temperature, not the temperature of the object they are measuring. This raises the question of how we can be certain that a thermometer measures the temperature of the object with which it is in contact. It is based on the fact that two systems placed in thermal contact, meaning heat transfer can occur between them, will reach the same temperature. That is, heat will flow from the hotter object to the cooler one until they have exactly the same temperature. The objects are then in thermal equilibrium and no further changes will occur. So basically, if you're using a thermometer to measure the temperature of just hot water, basically what's happening is the contact between the thermometer and the water will increase the reading on the thermometer until the surface of the thermometer and the water are at equilibrium. At that point, that is technically the temperature of the water. The systems interact and change because their temperatures differ, and the changes stop once their temperatures are the same. Thus, if enough time is allowed for this transfer of heat to run its course, the temperature a thermometer registers does represent the system with which it is in thermal equilibrium. Thermal equilibrium is established when two bodies are in contact with each other and can freely exchange energies. Furthermore, experimentation has shown that if two systems, A and B, are in thermal equilibrium with each other, and B is in thermal equilibrium with the third system, C, then A is also in thermal equilibrium with C. This is called the zeroth law of thermodynamics, and it's demonstrated here. It's basically what we just went over here. So basically you have A and B together, put them together, and if you put in C, then all three of those are in thermal equilibrium. You can pretty much picture, again, hot water with a thermometer. Let's say you put some ice into that water. Eventually, when that whole mixture is at thermal equilibrium, that would be the temperature that is given by the thermometer. Eventually that those ices are going, or those ice cubes are going to, melt. And at that point, little by little bit, you will see that temperature drop from the hot water because of the ice cubes. So that temperature that you're reading at every single point in time is the thermal equilibrium of the entire mixture. We also have thermal expansion. Thermal expansion joints like these in the Auckland Harbour Bridge in New Zealand allow bridges to change length without buckling. So here, these are changing links between the bridges, between the connections, without it really moving. The expansion of alcohol in the thermometer is one of many commonly encountered examples of thermal expansion. The change in size or volume of a given mass with temperature. So basically like that alcohol thermometer we saw at the very beginning. Hot air rises because its volume increases, which causes the hot air's density to be smaller than the density of the surrounding air, causing a buoyant upward force on the hot air. The same happens in liquids and gases, driving natural heat transfer upwards in homes, oceans, and weather systems. Solids also undergo thermal expansion. So a definition of thermal expansion, what is the underlying cause of it? An increase in temperature implies an increase in kinetic energy of individual atoms. Remember back when we were going over kinetic energy, like I said, all energy is conserved. Sometimes we lose it in thermal energy. This is where it would go to. In a solid, unlike a gas, the atoms or molecules are closely packed together, but their kinetic energy in the form of small rapid vibrations pushes neighboring atoms or molecules apart from each other. This neighbor-to-neighbor pushing results in a slight greater distance on average between neighbors and adds up to a larger size of the whole body. For the most substances under ordinary conditions, there is no preferred direction, and an increase in temperature will increase the solid size by a certain fraction in each dimension. So down here we have linear thermal expansion. That's the change in L is proportional to the length L. The dependence of thermal expansion on temperature, substance, and length is summarized by this equation. So you have the change in L, which is that's dignified here, equals alpha L and delta T, where delta L is the change in length, delta T is the change in temperature, and alpha is the coefficient of linear expansion. We'll get into those in a second. So you see that the longer time goes, so let's say you start at 0, you take about a 10-second reading, so you have about 10 seconds there. The longer the time is, the potentially longer the change in length is. Okay, so here we have our first example. The main span of the San Francisco Golden Gate Bridge is 1,275 meters long at its coldest. The bridge is exposed to temperatures ranging from negative 15 degrees C to 40 degrees C. What is the change in length between these temperatures, assuming that the bridge is made entirely of steel and has a coefficient of linear expansion of alpha equals 12 times 10 to the negative 6. Okay, so this alpha would go here. We know we have a changing temperature from 40, ranging from negative 15 to 40, and we have a length of 1,275. Okay, so our strategy is to use that same equation we just learned, and we are also given that coefficient of linear expansion, and the difference between the temperature is your final would be 40 minus a negative 15 degrees Celsius. So those negative minus would become a positive. So you have 40 plus 15. That would give you the 55 denoted here. So essentially just plug in. You plug in that 12 times 10 to the negative 6 times 1,275 meters times your 55. And that'll give you 0.84 meters. That is a changing length. Okay. So notice that the linear expansion coefficient is per C, per temperature. So you have to make sure that those temperature units cancel out. The only thing that should be left is meters, which is distance unit. So although not large compared with the length of the bridge, this changing length is observable. It is generally spread over the many expansion joints so that the expansion at each joint is small. So you won't be able to observe it with, you just looking at the bridge, but it's definitely there. That's how a lot of bridges are. Even the ones here in like Houston, if you go on a bridge on a very hot day, it'll actually be expanded very little at the joints, but it'll definitely expand to where none of the material that is made out of cracks. So for figure 13.11, we are giving delta A and delta V, and we'll go over those in a second. In general, objects expand in all directions as temperature increases. In these drawings, the original boundaries of the objects are shown by the solid lines and the expanded boundaries with the dashed lines. For A, area increases because both length and width are exposed or increases. So here we have our solid original, and this is the expanded version of it. Same thing with the square. The original is here, and the expanded is here. The area of the circular plug also increases. If the plug is removed, the hole it leaves becomes larger and with increasing temperature, just as if it was expanding, the plug were still in its place. So even though we are removing this part here, that hole that it would be left with would still expand. So for C, volume also increases because there's 3 dimensions increase. So remember, when something increases or expands in this case, it'll expand in every single direction. So it doesn't matter if it's 2D or 3D, it'll expand anyway. So these are the equations for the change in area with respect to temperature and the change in volume with respect to temperature. So here we have the linear expansion coefficients and the coefficient of volume expansion. That's what your alpha and your beta are, and these equations over here. So these two are pretty much given. You just have to know what type of material you're dealing with. So you have solids here, you have liquids here, and gases here. So you notice that there's really only one gas there. So for figure 13.12, the density of water as a function of temperature. Note that the thermal expansion is actually very small. The maximum density at +4, so positive 4 degrees Celsius, is only 0.0075% greater than that at the density at 2 degrees Celsius, and only 0.012% greater than that at 0 degrees Celsius. So it doesn't really budge as much. So now we go into thermal stress. Thermal stress is created by thermal expansion or contraction. Thermal stress can be destructive, such as when expanding gasoline ruptures a tank. It can also be useful, for example, when two parts are joined together by heating one in manufacturing, then slipping it over the other and allowing the combination to cool. Thermal stress can explain many phenomena, such as the weathering of rocks and pavement by the expansion of ice when it freezes. Railroad tracks and railroads can buckle on hot days if they lack sufficient expansion joints. Power lines sag more in the summer than in the winter and will snap in cold weather if the insufficient slack. Cracks open and close in plastered walls as the house warms and cools. Glass cooking pans will crack if cooled rapidly or unevenly because of the differential contraction and the stress it creates. Pyrex is less susceptible because of its small coefficient of thermal expansion. Nuclear reactor pressure vessels are threatened by overly rapid cooling, and although none have failed, several have been cooled faster than considered desirable. Biological cells are ruptured when foods are frozen, detracting from their taste. Repeating thawing and freezing insinuate the damage. Even the oceans can be affected. A significant portion of the rise in sea level that is resulting in global warming is due to the thermal expansion of seawater. So pretty much everything will contract and expand. Nothing is, forbidden from expanding or contracting. So thermal stress contributes to the formation of potholes. In Houston, we have a bunch of those. So now we move on to the ideal gas law, and I'm sure some of y'all have heard of this. Gases are easily compressed. We can see evidence of this by noting that gases have the largest coefficients of volume expansion. The large coefficients mean that gases expand and contract very rapidly with temperature changes. In addition, you will note that most gases expand at the same rate or have the same beta. This raises the question as to why gases should all act in nearly the same way when liquids and solids have widely varying expansion rates. The answer lies in the large separation of atoms and molecules in gases compared to their sizes, as illustrated in the next figure. Because atoms and molecules have large separations, forces between them can be ignored, except when they collide with each other during collisions. The motion of atoms and molecules at temperatures well above the boiling point is fast, such that gas occupies all of the accessible volume and the expansion of gas is rapid. In contrast, in liquids and solids, atoms and molecules are closer together and are quite sensitive to the forces between them. So here you see this is a representation of gases. Some atoms and molecules in a gas are typically widely separated as shown. Because the forces between them are quite weak at these distances, the properties of gas depend more on the number of atoms per unit volume and on the temperature than the type of atom. So for A, when air is pumped into a deflated tire, its volume first increases without much increase in pressure. So here we have a flat tire. As soon as we start pumping air, you'll see it fill, but that pressure won't increase as much. When the tire is filled to a certain point, the tire's walls resist further expansion and the pressure increases with more air. So once it's filled with a good amount of gas, then that pressure will start shooting up. Once the tire is inflated, its pressure increases with temperature. So a quick example for this would be, your tires between warm air or summer and winter. In the summer, you actually notice that your tires have higher pressures versus in the winter. That's why a lot of times whenever you start up your car and you see that tire pressure sign, that's because some of those pressures are too low and your car is, smart enough to tell you, hey, put pressures and push some air in your tires. And that's why it happens in colder temperatures. To get some idea of how pressure, temperature, and volume of a gas are related to one another, consider what happens when you pump air into an initially deflated tire. The tire's volume first increases in direct proportion to the amount of air injected without much increase in the tire pressure. Once the tire has expanded to nearly its full size, the walls limit volume expansion. If we continue to pump air into it, the pressure increases. The pressure will further increase when the car is driven and the tires move. Most manufacturers specify optimal tire pressure for cold tires. So from here, we go into the ideal gas law, which states your pressure, that's what your P signifies, times your volume, the volume it occupies, is equal to N, the number of atoms and molecules in gas, times your K, which is both main constant, that is K equals 1.38 times 10 to the negative 23 joules per Kelvin, times your temperature, your absolute temperature. So your absolute temperature has to be in Kelvin. Okay, so at room temperatures, collisions between atoms and molecules can be ignored. In this case, the gas is called an ideal gas, in which case the relationship between the pressure, volume, and temperature is given by the equation of state called the ideal gas law. The ideal gas law can be derived from basic principles, but was originally deduced from experimental measurements of Charles' law, that volume occupied by a gas is proportional to temperature at a fixed pressure, and from Boyle's law, that at a fixed temperature, the product PV is a constant. In the ideal gas model, the volume occupied by its atoms and molecules is a negligible fraction of V. The ideal gas law describes the behavior of real gases under most conditions. Note, for example, that N is the total number of moles of gas independent to the type of gas. So here we have PV equals nRT, and we have the numerical value for R in SI units is 6.02 times 10 to the 23rd times K here, which is that 1.38 we just found. So this is really your R, 8.31 joules per mole times Kelvin. In other units, we have R, calories per mole times Kelvin, and this is the 1.9. And in other units, we have 0.0821 liters times your atmospheric pressure over moles times Kelvin. You can use whichever value of R, and it's most convenient for that particular problem. So for figure 13.16, the air inside of this hot air balloon flying over Putrajaya, Malaysia, is hotter is hotter than the ambient air. As a result, the balloon experiences a buoyant force pushing it upwards. Pretty much how a lot of the air balloons work. So for example 13.6, suppose your bicycle tire is fully inflated with the absolute pressure of 7.00 times 10 to the 5th pascals, a gauge pressure of just under 90 pounds per inch squared, at a temperature of 18 degrees Celsius. What is the pressure after its temperature has risen to 35 degrees Celsius? Assume that there is no appreciable leaks or changes in volume. Okay. So our strategy, the pressure in the tire changing only because of the changes in temperature. First, we need to identify what we know and what we want to know, and then identify an equation to solve the unknown. So we know we have our initial pressure here with our initial temperature of 18 degrees C and the final temperature of 35 degrees C. We must find the final pressure, PF. So how can we use the equation PV equals nRT? At first, it may seem that not enough information is given because volume V and the number of atoms that are not specified. What we can do, though, is use the equation twice. You have the initial and the final, and if we divide PF VF by P naught V naught, we can come up with an equation that allows us to solve for PF. So here, since volume is constant, VF and V naught are the same, and they cancel out. Same as with N and K. So we end up going to PF over P naught equals TF over T naught. And you simply just multiply it by that initial pressure to the right. So we convert first the temperatures from Celsius to Kelvin. Use that equation we found out at the beginning. We want to find the change. So we have 18 plus 273. That'll give us 291 Kelvin. And 35 plus 273 Kelvin will give us 308. And then after that, we just plug in. We have the pressure initially times the temperature final over the temperature initial. And the final pressure would be 7.41 times 10 to the 5th pascals. So the final temperature is about 6% greater than the original temperature. So the final pressure is about 6% greater as well. Note that the absolute pressure and the absolute temperature must be used in the ideal gas law. So moles and Avogadro's number. It is sometimes convenient to work in a unit other than molecules when measuring the amount of substance. A mole, abbreviated by mole, is defined to be the amount of a substance that contains as many atoms or molecules as there are atoms in exactly 12 grams, 0.012 kilograms of carbon-12. The actual number of atoms or molecules is 1 mole, and it's called Avogadro's number, Na. In recognition of Italian scientist Amedeo Avogadro, he developed the concept of the mole based on the hypothesis that equal volumes of gas at the same pressure and temperature contain equal numbers of molecules. That is, the number is independent to the type of gas. This hypothesis has been confirmed, and the value of Avogadro's number is 6.02 times 10 to the 23rd mole. And this was one of the numbers we had discussed before as well. So now, same example, we have how many moles of gas are in a bike tire with a volume 2 times 10 to the negative third meters cubed, so about 2 liters, a pressure of 7 times 10 to the 5th pascals, a gauge pressure just under 90 pounds per inch squared, and at a temperature of 18 degrees Celsius. 13.9. Okay. So we have this equation, PV equals nRT. We have our pressure, we have our volume, we have a temperature that we convert into Kelvin, and we have our R. This is in moles per Kelvin. So we have PV equals nRT, and we want to find N. So we just divide by RT, and we are left with N equals PV over RT. And you plug in everything, and you just get 0.579 moles. So our convenient choice for R here is 8.31 joules per mole times Kelvin, because of our quantities are in SI units. Okay, that's the only reason we use that one. Like mentioned earlier, whichever one is more convenient to the problem, that should be the one you're using. Okay, so figure 13.20. When a molecule collides with a rigid wall, the component of its momentum perpendicular to the wall is reversed. A force is thus exerted on the wall, creating pressure. We have developed macroscopic definitions of pressure and temperature. Pressure is the force divided by the area on which the force is exerted, and temperature is measured by with a thermometer. We gain a better understanding of pressure and temperature from the kinetic theory of gases, which assumes that atoms and molecules are in continuous random motion. So here the figure shows an elastic collision of a gas molecule with the wall of a container so that it exerts a force on the wall by Newton's third law. Because a huge number of molecules will collide with the wall in a short time, we observe an average force per unit area. These collisions are the source of pressure in a gas. As the number of molecules increases, the number of collisions and thus the pressure increase. Similarly, the gas pressure is higher if the average velocity of molecules is higher. Gas in a box exerts an outward pressure on its walls. A molecule colliding with a rigid wall has a direction of its velocity and momentum in the x direction reversed. This direction is perpendicular to the wall. The components of its velocity and momentum in the y and z directions are not changed, which means there is no force parallel to the wall. Okay, so here you just see the inside of a box here. You see that it's coming in from here, but your x direction changes. However, your y direction or velocity should not change really. Okay, and this just signifies your x direction is this way, your y direction is this way, and your z direction is along the wall. With some clever algebra, we can produce the result that an average kinetic energy of a molecule is directly related to absolute temperature. So we have kinetic energy equals 1/2 mv squared, stated before in earlier chapters. So this equals 3/2 kT. This is your thermal energy. Okay. This equation is a molecular interpretation of temperature and has been found to be valid for gases and reasonably accurate in liquids and solids. It is another definition of temperature based on an expression of a molecular energy. It is sometimes useful to rearrange this equation and solve for the average speed of a molecule in a gas in terms of temperature. So solving for your B here, you'll get 3 kT over m, square root of that, where your V, RMS, stands for root mean square. So it's just this B squared and square root. So here for figure 13.10, you have A. There are many molecules moving so fast in an ordinary gas that they collide a billion times a second. So here in B, individual molecules do not move very far in a small amount of time, but the disturbances like sound waves are transmitted at speeds relative to the molecular speeds. So an example for this one would be, what is the average kinetic energy of a gas molecule at 20 degrees C at room temperature? For B, we're looking for find the RMS speed in a nitrogen molecule N2 at this temperature. Okay, so we have Ke equals 1/2 mv squared, which is equal to our 3/2 kT. So first, change that T, which is 20 degrees C, to Kelvin. So you have 293 K. So for kinetic energy, we know to pretty much insert the 3 over 2 times your K, which is 1.38 times 10 to the negative 23 in this case, times your temperature. So that'll give you 6.07 times 10 to the negative 21 joules. That is our kinetic energy. So now finding the speed of this, we use that VRMS equation. But first we must find the mass of a nitrogen molecule. Using the molecular mass of nitrogen, N2, from the periodic table, we can say 2 times 14.0073 times 10 to the negative 23 kilograms per mole over our mole Avogadro's number. So our mass of this N2 is 4.65 times 10 to the negative 23rd kilograms. So very, very small. And once we know that, all we have to do is plug in. And this will give us 511 meters a second. So that's how fast that molecule is moving in that temperature. It's pretty fast. So for here, sketch of volume versus temperature for a real gas at constant temperature. The linear straight line part of the graph represents the ideal gas behavior. So this part right here. Volume and temperature are directly and positively related, and the line extrapolates to zero volume at negative 273.15 degrees C, or absolute zero. When the gas becomes a liquid, however, the volume actually decreases perceptually at the liquefaction point. So it would be here. The volume decreases slightly once the substance is a solid, but it never becomes zero. So here we're going to go over the triple point, which is the phase diagram PT graph, pressure versus time. For water, note that the axes are nonlinear and that the graph is not to scale. The graph is simplified. There are several other exotic phases of ice at higher temperatures. So here we know that temperature in C, we have this solid up to 100 degrees. We have a liquid when the pressure is between 1 to about 218, and between these temperatures right here. And then it's V, volume, whenever our temperatures are between 100 to 374, and our pressure is from 1 to 218. So here's a little bit more descriptive here. We have solids here between 100 and 100 K pascals to 100 MPa. We have different phases from solid, liquid, and vapor. We have our boiling point here. We have our triple point from solid, liquid, and vapor triple point, which is 273 K and at 611.657 pascals. We have our temperature readings over here from 0K to about 650K. Down here it's in Celsius. So this is a good way to figure out from where H2O becomes from solid to liquid to gas, which is vapor. So phase diagrams, the plots of pressure versus temperature, provide considerable insight into thermal properties of substances. There are well-defined regions on these graphs that correspond to various phases of matter. So PT graphs are called phase diagrams. Using these graphs, if you know the pressure and temperature, you can determine the phase of matter. These solid lines, boundaries between the phases, so that would be here, here, and here, indicate temperatures and pressures at which the phases coexist. That is, they exist together in ratios depending on the pressure and temperature. For example, the boiling point of water is 100 degrees C at 1 atmospheric pressure. As the pressure increases, the boiling temperature rises steadily to 374 degrees C at a pressure of 218 atm. A pressure cooker or even a covered pot will cook food faster because water can exist as a liquid and the temperature is greater than 100 degrees C without all boiling away. The curve ends at a point called the critical point because at higher temperatures, the liquid phase does not exist at any pressure. The critical point is also called the critical temperature. The critical temperature for oxygen is about 118 degrees C, so oxygen cannot be liquefied above this temperature. Similarly, the curve between the solid and the liquid regions gives the melting temperatures at various pressures. For example, the melting point is 0 degrees C at 1 atm for water as expected. Note that at a fixed temperature, you can change the phase from solid, which is ice, to liquid, which is water, by increasing the pressure. Ice melts from pressure in the hands of a snowball maker. From the phase diagram, we can also say that the melting pressure of ice rises with increased pressure. When a car is driven over snow, the increased pressure from the tires melts the snowflakes. Afterwards, the water refreezes and forms another ice layer. At sufficiently low pressures, there is no liquid phase, but the substance can exist as either gas or solid. For water, there is no liquid phase at pressures below 0.00600 atm. The phase change from solid to gas is called sublimation. It accounts for large losses of snowpack that can never make it into a river, the routine automatic defrosting of a freezer, and the freeze drying process applied to many foods. Carbon dioxide, on the other hand, sublimates at standard atmospheric pressure of 1 atm. The solid form of CO2 is known as dry ice because it does not melt. Instead, it moves directly from a solid to a gas state. All three curves on the phase diagram meet at a single point, the triple point, where all three phases exist in equilibrium. For water, the triple point occurs at 273.16, a little bit above 0 C, and is the more accurate calibration temperature than the melting point of water at 1 atm or 273.15, which is 0 degrees Celsius. So, like mentioned before, for equilibrium, these show for A, the rates of boiling and condensation are equal at this combination of temperature and pressure, so that the liquid and gas phases are in equilibrium. For B, at a higher temperature, the boiling rate is faster, and at the rates at which molecules leave the liquid and enter the gas are also faster. Because there are more molecules in the gas pressure is higher, and the rate at which the gas molecules condense and enter the liquid is faster. As a result, the gas and liquid are in equilibrium at this higher temperature. So you see here it's at a lower temperature, here it's at a higher. Condensation and the vaporization are lower here versus the one in B. Also notice that the pressure here is lower versus the one in B. Liquid and gas phases are in equilibrium at the boiling temperature. And if a substance is a closed container at a boiling point, then the liquid is boiling and the gas is condensing at the same rate without net change in their relative amount. Molecules in the liquid escape as a gas at the same rate which gas molecules stick to the liquid and form droplets and become part of the liquid phase. The combination of the temperature and pressure has to be just right. If the temperature and pressure are increased, equilibrium is maintained by the same increase of boiling and condensation rates. So for vapor pressure, for A, we have, because of the distribution of speeds and kinetic energies, some water molecules can break away from the vapor phase even at the temperatures below the ordinary boiling point. So you see here, you have all these vapor molecules here, and they're slowly escaping here. But if the container is sealed, evaporation will continue until there is enough vapor density for the condensation rate to equal the evaporation rate. This vapor density and the partial pressure it creates are at the saturation values. They increase with temperature and are independent of the presence of other gases such as air. They depend only on vapor pressure of water. Vapor pressure is defined as the pressure at which a gas coexists with the solid and liquid phase. So Dahl's law of partial pressure. Partial pressure is defined as the pressure a gas would create if it occupied the total volume available. In a mixture of gases, the total pressure is the sum of partial pressures of the component gases, assuming ideal gas behavior and no chemical reactions between the components. This is known as Dahl's law of partial pressures, after the English scientist John Dalton, who proposed it. Dahl's law is based on the kinetic theory, where each gas creates its pressure by molecular collisions independent of other gases present. It is consistent with the fact that pressures add according to Pascal's principle. Okay, so that is the end of chapter 13.